When a new feature arrives on the backlog today, the engineering muscle memory has shifted. Instead of asking what data structure or formal algorithm a task requires, the default response is to ask which model to prompt. We see simple user requests bypassing traditional validation layers entirely, routed straight into a large language model. The request is processed, and the output is usually correct. But the architectural cost is severe. An operation that should have executed locally in nanoseconds for free now incurs a network round trip. The wait time spikes into the hundreds of milliseconds, and the per-call cloud bill ticks upward. The temptation to build this way is obvious. Large language models are highly capable generalists. You can hand a single model, a parsing task, a classification task, and a summarization task, and it will return plausible outputs for all three without any bespoke feature engineering or retraining. But deploying a generalized machine learning model with billions of parameters to execute a rigid, fully definable instruction is the computational equivalent of crushing a walnut with an industrial forging press. It works, but it requires a staggering expenditure of energy to achieve a simple result. When engineering teams replace fast, predictable code with non-deterministic API calls, they accumulate a specific type of technical burden: probabilistic debt. You are taking a function that used to offer mathematical guarantees and introducing a permanent source of entropy. Conflating a model's broad linguistic capability with computational superiority is an architectural error. A system built entirely out of generalized probabilistic calls will inevitably degrade under high user volume. In The Hitchhiker's Guide to the Galaxy, the operators of the supercomputer Deep Thought wait 7.5 million years for the answer to the ultimate question of life, the universe, and everything. The computer returns the number 42. The answer is useless because nobody understood the question they were asking. Evaluating a system solely on the accuracy of an LLM's output misses the prior architectural decision. The more significant choice happens before the prompt is even written, deciding whether a language model belongs in that execution path at all. Computer science is the study of what can be computed, how efficiently, and with what guarantees. The arrival of the transformer architecture overshadowed formal algorithms and complexity theory, but it did not supersede them. A regular expression resolving in microseconds or a B-tree index locating a record in logarithmic time are not legacy techniques waiting to be modernized by AI. They are the permanent, load-bearing walls of any production system. The LLM sits on top of them. The highest leverage skill for a technical leader today is not knowing how to construct the perfect prompt. It is knowing exactly when to keep the prompt away from the codebase. This chart shows the spectrum of certainty. The left is reserved for tasks specified in advance. Classical algorithms handle these instantaneously, with zero marginal cost. The right is for open-ended generation. The LLM API sits here, providing flexibility at the cost of high latency. This page identifies exactly what happens when you force a left-side task through a right-side tool. The system pays 3 compounding penalties. First is the cost penalty. You pay a per-call fee to a cloud provider to execute logic your own local CPU could process for free. At a scale of 1 million operations a day, the financial waste is massive. Second is the latency penalty. Converting a string format using a local function takes nanoseconds. Routing that string to a language model introduces hundreds of milliseconds of network delay, injecting visible lag into a background task that should be imperceptible. Third, and most critical, is the reliability penalty. If a contract between producer and consumer requires an exact identical output for a given input, relying on a probabilistic model guarantees failure. Given enough volume, the model will eventually produce a hallucination or a format error. To see these penalties in action, look at the task of email validation. The system must determine if a user-submitted string matches the RFC 5322 standard. A regular expression solves this in under a millisecond with a mathematical guarantee of accuracy, for free. The same validation routed to an LLM requires a network trip, 300 milliseconds of latency, and costs $24 per million calls. Consider a slightly more complex task: named entity recognition, or extracting names, organizations, and locations from an incoming stream of customer support tickets. This table presents 2026 production benchmarks, evaluating NLP pipelines against LLMs. Because support tickets represent a stable domain, a self-hosted spicy pipeline delivers comparable accuracy to the LLM. But classical pipelines execute in single-digit milliseconds and cost 17 to 27 times less to operate. The language model does mathematically outperform the classical tools in one specific scenario: out-of-domain accuracy. If you need to extract entities from highly novel text, like cutting-edge biomedical research where no prior training data exists, the LLM's generalized knowledge wins. The data proves the rule. Train and deploy the highly efficient, specialized tool for your known, high-volume domains. Reserve the expensive, generalized language model exclusively for unpredictable edge cases. This logic applies directly to routing high-volume user traffic, like classifying incoming messages for a customer service chatbot into 30 predefined categories. The classical approach uses a TF-IDF vectorizer paired with a support vector machine. Once trained on historical logs, this model executes locally in milliseconds. It costs nothing at inference time, and it outputs a strict confidence score that engineers can use to trigger automated workflows. Replacing that vectorizer with a few-shot LLM prompt introduces immediate network latency and continuous per-call costs. Worse, it exposes the routing logic to hallucinations, where the model might generate a category name that does not exist in the canonical database. Placing non-deterministic logic at the front of a high-volume pipeline is structural sabotage. As volume scales, inconsistencies compound, requiring manual error handling to survive. Using a language model for strict high-volume classification creates structural fragility for no measurable gain. Unless the intent categories are changing weekly, this choice introduces unnecessary cost, latency, and non-determinism into the system's core logic. Critiquing poor architecture is easy. Building systems correctly requires a practical routing framework that teams can apply to every single feature added to the product backlog. This diagram shows the conductor's decision tree. It is a mandatory gauntlet designed to exhaust cheaper computational options before utilizing generative AI. The first gate is strict determinism. If the required output must be identical every single time, the task routes to regex, SQL, or a classical algorithm. If it requires semantic understanding, but output categories are known and stable, it routes to heuristics or classical machine learning. The final gate measures scale. If semantic understanding is required at high volumes, over 100,000 operations a day, you build a spicy pipeline. The LLM API is strictly reserved for the low-volume, highly complex tasks that survive all three filters. This tree acts as the Hippocratic oath for software engineering. First, do no harm to your system's efficiency. This decision tree creates a multi-layered pipeline. A top tier of deterministic triage catches the vast majority of requests at near zero cost. A middle tier of specialized semantic models handles linguistic tasks. Only a tiny fraction of edge cases trickle down to the LLM. This architecture guarantees a production system that is measurably faster, significantly cheaper to operate, and far easier to audit than a monolithic generative application. Treat a frontier language model as a consultant with a PhD in every subject. It can bridge knowledge gaps across dozens of fields, from distributed systems architecture to Jacobian drama, but its role remains strictly advisory. The optimal relationship is Socratic Turing. You provide the intent, the architectural constraints, and the empirical experience of having shipped real products. The machine provides the code translation and explores the surface area of the problem. The machine has read every textbook in existence, but it knows absolutely nothing about your production environment. Master the models, extract their immense value, but do not forget the computer science that keeps the servers running.